Yes?
Yes.
Okay. Are we?
Now we're on time. And
just about on time.
We are all eager to hear Sam Lindley speak about high-level effect handlers in C++.
In C++, yes. Yeah, so I apologize for lowering the tone. About 25 years ago, I was actually a professional C++ programmer, and I haven't really done any C++ programming since then, and the language has changed quite a lot. But we were interested in taking effect handlers and seeing how far we could go with trying to implement them in quite a different setting to where they'd been used before, in an imperative language, in a mainstream imperative language with no garbage collection, where people don't want to be writing functional code with tail calls, but would prefer to write loops and such like. And this is joint work with these other people who were all at Huawei when we did the work. Maciej has subsequently left and is now at Standard Chartered. And he really did most of the work. So if you have any technical questions about C++, I may not be able to answer them. I'm very glad to be in this session because we've already had a whole load of stuff about effect handlers. But I am going to begin with my sort of high-level sales pitch for why effect handlers are a good thing. And then I'll move on to some examples in C++ to illustrate our library. And I'll talk about a bit more about the design and implementation and give you some numbers as well. Right. So my starting point for thinking about effects and effect handlers is, well, we have nice ways of talking about programs, at least in the functional programming community, where we think a program is a black box. It takes an input to an output, and lots of nice theoretical results you get there. But in the real world, we need more. Programs need to interact with the context in which they're running, and we normally do that via some sort of runtime or operating system. Effects are everywhere. I probably don't need to spend too much time on this, given that we've had all this background. But typically ad hoc and hardwired. So in particular in a language like C++, it has all kinds of effects, but it doesn't have a natural way of abstracting over them or defining your own new effects. And that's where effect handlers come in. So my colleagues, Gordon and Mattia, introduced them in a very theoretical setting. But as I hope some of the two previous talks have illustrated, they're quite practically useful as well. In particular, they give you a way of composing and customizing your user-defined effects. And crucially, they give you direct access to the context in which you're running. So similarities with other abstractions like resumable exceptions, monads, delimited control. I guess the customizability and the composability is what sets them apart maybe from prior abstractions. And they also having significant industrial impact. So there's a number of different projects outside of research, where they've been used to great effect. I also like this picture of effect handlers, kind of composable user-defined operating systems. So if you take the rectangle, I wonder if there's kind of point there. This is kind of your computation. We can kind of expand this, and then we have lots of little these boxes with the gears in. They represent effect handlers, little user-defined operating systems, and they implement some kind of effectful interface illustrated by these shapes, and you get the stacklet structure, which is similar to the way in which exception handling works. So this is a very, very high-level picture of what effect handlers are. Now I'm going to just jump straight in and show you some C++ code. I'm starting with a state example, not because this is what we should be using effect handlers particularly for, particularly in a language like C++, but because it's a simple example and allows me to show you what the syntax looks like. So in our library, you define an effect, we call them commands, which correspond to effectful operations, as a class or a struct that is derived from the command subclass. And it can have whatever payload it likes, and in the template brackets, you indicate the return type of the command. For convenience, we tend to define wrapper functions, which invoke each of these commands. And then you can just use these things just like normal functions. And I can write some sort of computation in terms of these. This is just an increment function, and it just looks like normal kind of C code, C++ code. At this stage, though, we've not said what it actually means or does. And the way in which you do give a meaning to this is by searching through a stack of handlers, much like the way in which we handle exceptions. So, come on. Right. So here's what a handler looks like in our library. It's a class. It's derived from the handler class, and you have well, a variable number of parameters. The first two are I think this is the answer type of the computation you're handling, and then the answer type of the result of handling it. And then you have a collection of all the commands. And under the hood, it's using horrible multiple inheritance tricks to get this to work. And then inside here, for each command that you want to handle, you just define a method. And the crucial difference between this and the way in which exception handling works is that you get given the resumption as well as the command and any payload it has. And in this case, you don't really need to do anything interesting here. We're just going to always invoke that resumption in tail position. There's some funny stuff going on with these move constructors. The way I see that is as a sort of very hacky way of getting the kind of benefits you get from something like Rust or a linear type system. It doesn't need to allocate a new object. You can reuse it. Only get a return clause where you can say what to do at the end of your computation. Here, it's just the identity. So this is the basic thing, and our goal here was really just to see, well, can we implement handlers in a reasonable way in C++? There's been prior work in implementing similar libraries in C, and they're incredibly unsafe, not really designed for users. This is not too terrible. By default, the way in which the matching actually takes place is it goes up the stack that we're maintaining, and it uses runtime type information in order to work out which handler to pick, which is a bit inefficient. But to use it, yeah, you just take your computation and you call handle on it. And I think there are lots of trade-offs here, but it's what we have so far is nothing that would be particularly surprising, I hope, to a C++ programmer in terms of usability. My next example is a much more interesting one, and the kind of target application that we have in mind. So where we actually want to capture the resumption and not just run it immediately, but use it later. So this is lightweight threads. So the idea is we have a yield command, which allows you to yield control to another thread, and a fork command, which allows us to create a new thread. Again, we're doing this thing with the wrappers. And you might write a computation like this that's going to fork off a couple of threads and interleave the computations and print some things out in between. And then here is how we might write write a handler for it. What's maybe interesting is that the bulk of the work here is actually taking place in this scheduler loop, which is not concerned particularly with the handling of the commands. All that the handling of commands does, well, if we get a yield, we just stick the current resumption into our queue. If we get a fork, we add both the new thread and the current resumption. And the scheduler loop just keeps on running. And it looks very much like you might expect a scheduler loop to look in a language like C++. So this is what we hoped to achieve, and it looks okay. Right. And then, yeah, you can just invoke that static method. And it does what we'd expect. I'm going to show you a few more examples from the library to just show how you can make it a little bit more ergonomic. So one thing, let's see, what do we have here? This is an alternative version of the state handler. If you have a handler in which the return clause is the identity, as it was with the state, then you can use the flat handler class, which automatically fills that in for you, so I don't have to write a return clause. And then if your commands are being handled, if they're tail resumptive, we call them plain commands, then you don't need to bother faffing around with the resumptions at all. And this is just fairly boring abstraction over the commands as if they were just normal functions. Okay. Another variation we have on these clauses is the no resume modifier, and that's just specifying the case where you don't want to invoke the resumption. So that's if you want something like an exception. So in this case, we're imagining we extend this scheduler so that it also handles a kill command, which isn't going to invoke the resumption. It just kills the current thread. I'm now going to show you a more involved example. This illustrates the composition of handlers. So supposing we've got our lightweight threads, we now want to build actors on top of that. So by actors, I mean we have, well, these 4 commands. We can spawn a new actor process. We can get the process ID of an actor process, and we can send messages to some other actor or process given by the process ID. And we can receive messages. One thing you'll see going on here is that we've got this universal type for our messages under the hood, but in our wrapper functions, we can actually do a bit better than that. So you can use the template parameters and do a cast in the appropriate place. And then now we can define a handler which is going to handle these. Are there some of them? Oh no, they're there on that line. It handles these actor commands, and you see that they're actually all plain. We're always going to invoke the resumption in tail position, but it's handling them by invoking other commands, fork and yield. Actually, do we have a yield? Well, certainly fork, anyway, which will then be handled by the outer scheduler handler. And it just nicely composes together. I don't have an example of actually running it, but composition works. Oh yeah, this example was just to illustrate the pattern I showed you before, where you often have, you define, so you can do async await as well. We could define an await command, and again, you have a sort of universal type for your futures. But in the wrapper function, we can still make this statically typed for the purposes of the user. Now, I'm very glad that I'm giving this talk immediately after UU, because we also have named handlers in C++. And we do, it'd be much, I think it'd be harder to do the run st trick in a language like C++. So we didn't bother at all. We just have the unsafe. I mean, it's not that unsafe, actually. If you try and perform a command using a handler that's not in scope, it's just like an unchecked exception reaching the top of the stack. I mean, you'll just get an unhandled exception. It's not too unsafe. So yeah, here the example is we want to implement a generator. And the command we defined is just going to yield a value, this yield thing of type T. But our wrapper function is taking, our names are it's a bit hacky. The names are just in 64s. And instead of the normal invoke command, you pass in a label. For this particular example, and actually quite a lot of the examples we care about, it doesn't matter so much what's going on under the hood here, because the user is not going to be exposed to any of this at all. Sort of for the expert library author to worry about. So as I said, the label is going to identify the handler by name. Another side effect of this is actually, if we're handling it by name, then we don't need to do this runtime type information stuff. We can do a static cast instead, which is a bit more efficient. Okay, I don't really want to dwell on the details of this, but yeah, you could define a handler that handles this effect, and it creates this particular data type. The important point is when you actually define the generator itself, all of the use of the handler is hidden inside the constructor for the generator, and you pass it. It passes in a higher order function that represents what you want your yield to do. Kind of ignore all that. When you come to use it, there's no mention of commands or handlers, and the user doesn't need to know anything about them at all. The main reason actually here we were using a name is if we had multiple generators somehow interleaved, then you can't get any accidental capture. We're guaranteeing that this generator is always going to be handled by its handler. Okay, so there's my array of examples. I'm just going to flash up this slide to summarize the design of this library. Some of these things I've covered, some of them are maybe more for the benefit of people who are familiar with effect handlers. I guess crucially, our handlers are deep handlers and they're affine. The way we implement this is on top of a library based on fibers, and you cannot duplicate your continuation. You'll just get a runtime error. Anything else I wanted to pick out here? I think I've covered everything. I'll just move on. This is the rough picture of how the inheritance hierarchy works. So you have this multiple inheritance thing going on with all these command clauses. I guess that's the main thing. And then underneath, we're using this boost context library, which has these fibers, which are not in any way, they're just like flat, lightweight threads. So each one has their own stacks. So, although we're interested in plugging in other backends, here's an illustration of what happens when you invoke a command. You have a stack, a flat stack like this that has handlers, frames, and so this is like exception handling. And when you invoke this command, it's going to traverse the stack. I think it's going down, yeah. And that's going to capture this delimited continuation, this resumption. And then it will call the handle command method. In fact, we don't represent it quite like that. It's a more nested structure with pointers in here, which has certain technical advantages I can't remember. Other details here. We do make use of reference counting, and there's some subtle issues to do with managing the lifetime of these handlers and resumptions. In general, they can escape. If you know that they're not going to escape, we have this optimization that you can use, which means you don't have to. You can deallocate them or reuse the memory early. I'm now going to just finish by showing you some benchmarks. So we didn't really focus very hard on trying to make this fast, but we thought we should at least compare it with some existing things anyway. So this is about the worst possible thing you could do with handlers. I think this benchmark basically just counts up to 1 million or something using state. So it's doing something very inefficient. In particular, the general version is the one that's actually capturing the continuation every time you do this. So that's very, very slow compared to just doing a for loop with a global variable. But if you use the plain modifier, then it's only 10 times slower. Oh, sorry, that's not our library. This is a different library we're comparing with, which has the same. So this is Dan Lyon's C library, which is interesting. It's sort of unusable, I think, by humans, but it's good as a target language for C. Whereas ours, we intend to be usable by humans. But you see a similar. We doing the plain thing helps certainly. I'm not sure what the static meant there. Oh, I think that was with named handlers, and then this was the no manage, and then finally the plain. Oh, and we did the same. We got similar results with another C++ implementation. Here's a more interesting experiment. We also compared the generator example with the C++ coroutines, which are implemented in a completely different way by compiling away into a state machine. So this example is doing a tight loop, and we're way worse if you're just using generators in a very boring way. But if you have a generator that, say, traverses a tree, as in this case, then the scheme where you compile into a state machine doesn't really scale. Well, you can see it's linear, where in the number of nodes. Whereas we actually start really poorly, but as the number of nodes increases, we're completely stable. So that's illustrating a fundamental difference between this stackless compilation method and the stackful one. Okay. I think I'm almost done here. Yeah, so I'd encourage people to play with this library. You can download it there. It was really just a sort of experiment to see, well, can we make this stuff work in a language like C++? And our conclusion is, yes, we probably can. There's plenty more scope for working out, well, can you actually make it performant enough that people would want to use it? Though I would say, we didn't actually test it on the kind of applications that it's designed for. We only tested it on the worst cases. So I would imagine if you're using it for actual concurrency, it might actually be usable. Anyway, thank you.
Thank you. Questions from the C++ experts? Yeah, can you go first here right here in the middle?
So if I understand correctly, this is based on boost.context, which essentially gives you a kind of call CC in C++. Is that
It gives
correct?
you, sorry, what?
A kind of call CC primitive in C++?
It does not give you a call CC primitive. No, it gives you something more like coroutines or, well, a low-level thing. It doesn't. Okay, I guess it is sort of like call CC in that it captures. Yeah, you're sort of capturing the whole continuation. So
except you can only use a continuation once, maybe.
Yeah.
So
I suppose in that sense, yes.
So, but if that's the case, then why is it why is it surprising that you can implement effect handlers?
Right. So the difficulty.
Given call
So
CC,
the prior work in this area have mainly been implementing effect handlers in C, and you can do it perfectly well. It's the main point was to see that we could do it in a way that was ergonomic and usable. That was our main concern, really, and sort of type safe to the degree that a C++ programmer might expect. And we think it probably is, but whereas the prior work, like I said, the stuff done in C is incredibly fragile. It's great if you know exactly how to plug things together, but very dangerous. Whereas this is relatively usable and safe, I think. Yeah.
So there are further questions?
Yeah. Yes, I noticed you kept having to define those wrapper functions. Is it possible to automate that in some way?
Easily, yeah. You could easily automate it.
With
some
the
sort
C++
of
like templates.
Oh.
I mean, like not like actual generate C++ code, but
no, I don't think
you'd
want to do that. I don't think you'd want to do that. but yeah, maybe. Yeah.
Thanks very much for an interesting talk. So I was quite interested to see when you were using runtime type information. Do you have a formal account of that, or is there an existing formal account of that in the literature?
Well, we use runtime type information whenever you use unnamed handlers. So, like most of the time. I mean, that's just a limitation of, well, having to hack something on C++. And that comes back to the first question here of getting the thing to be safe at all required something like that. In C implementations, you just sort of do a cast to void star and hope.
Sure, but I mean, is there as an implementation strategy, I get what you mean. Is there anything interesting formally there?
Don't know. Not something we thought about.
Okay.
Maybe.
Thanks.
No, good question. Yeah.
So there's a question there in the back. Oh, sorry.
Hi, so did you think about just using C++'s coroutines facilities to implement this rather than using a boost library?
I think you could do that. It would be, yeah, that might be an interesting exercise. It would probably work well for the use cases that we care least about, I think. Because as I showed with that last benchmark, once you start doing something with more structure, C++ coroutines fall over. But yeah, it'd be a worthwhile experiment, I think.
I think there was one in the back here. No? Okay. I thought I saw another question. Ah, there's one over.
Yeah, I wanted error messages because you encoded that effect system by using templates. So what kind of error messages do you get if you write some wrong program using your library? Well, with respect to type system.
Yeah, I'm probably not the person to ask. I've not used it in anger, really, but from what Maciej tells me, the error messages didn't seem any worse than the ones he was used to with C++. Yeah, but I could imagine with all this multiple inheritance stuff going on, it might be problematic. Yeah.
So here, Dominic.
Yeah, as a follow-up, are you using C++ concepts at all to maybe improve error messages and make explicit the assumptions you have on?
Not as far as I'm aware. Yeah. Yeah. Oh, one thing relating to that actually is the library does not play well with exceptions, C++ exceptions at the moment, and there's a good reason for that. It's because it is implemented on top of this Boost context library, and that doesn't. You'd have to do something clever to make sure that they actually propagated through the end of a fiber. And this is why I would not actually advocate anyone implementing effect handlers this way if you're starting from scratch. There are better ways to implement effect handlers. Which is also why we'd like to experiment with, for instance, plugging in this libmprompt library as an alternative backend. Because that's built on delimited control, which is a much nicer low-level abstraction because it composes with existing effects, existing control effects like exceptions.
Thanks. So it seems that memory management becomes more difficult because, for example, continuation can be discarded, but it may contain pointers, the right pointers. So, for example, so does standard memory management in C++, like a smart pointer, works well?
Yeah, I mean, we're using reference counting, and that is fairly standard in C++. So I don't think it's any better or worse than what people are used to. This one here.
Yeah, I think we should conclude now.
Yeah.
Well, thank you for the talk. Thank you for the discussion. And